Okay, folks, so we just walked our way through why ATP is considered a high energy molecule. What we're going to see over the next few weeks in class is that when we do something like cleave a bond in ATP and release all of this energy, we need to harvest that energy to do something with. If we just cleave the bond and release the energy and nothing happens, that energy release is wasted. And what the cell does is it's going to conserve that energy and use the energy released for something else. So let's just have a bit of a foreshadowing here of things we're going to learn over the next few weeks so that when we see them, we're more comfortable with them. So, quick reminder, folks. When are reactions spontaneous or when do reactions proceed? When the overall delta G is less than 0. Recall, a negative delta G is spontaneous, is favorable. And so there are many reactions that we'll see where the reaction itself releases energy, has a negative delta G. But we'll also see along the way that there are some reactions, or even some kind of half reactions, that require an input of energy. So when we see a reaction performed in our bodies that requires an input of energy, we should think, okay, it's probably linked up or coupled to a reaction that releases energy. So let's have an example here on the screen for us to think through. Let's imagine that the delta G for reaction 1 is positive, right? This positive delta G would indicate that reaction 1 is not spontaneous or not favorable. What if we couple reaction 1 to reaction 2? Well, if reaction 2 is negative enough, if it releases enough energy, reaction 2 will go ahead and proceed, and it'll kind of pull reaction 1 along with it. Why does this make sense? Well, folks, let's look at reaction 2. Reaction 2 takes the reactants or the substrates D and E, and it converts them into F and G. So we're using D to make F and G. Notice how reaction 1's product is D. Think about Le Chatelier's principle now. If we're using D to make F and G, the concentration of D decreases. Well, reaction 1 will then be pulled along by Le Chatelier's principle. If the concentration of products decreases, the equilibrium shifts to make more products, right? So we'll keep this in mind when we think about reactions. They're spontaneous if the delta G is negative, but if there is an input of energy required, we're going to probably link it up or couple it to a reaction that is negative. And we can see this in some kind of half reactions that we'll learn about in glycolysis. The first step in glycolysis is performed by an enzyme called hexokinase. We will see this very soon. What I want you to get from this slide, though, is what's happening with the delta G. So the overall reaction has a delta G of negative 16.7 kilojoules per mole. There are kind of two parts to this reaction. One part of the reaction is combining a phosphate with a glucose. In order to put a phosphate on a glucose to perform a phosphorylation, we're going to need an input of energy of 13.8 kilojoules per mole. Well, what if we couple this half reaction with the hydrolysis of ATP? Chopping ATP into ADP and phosphate releases 30 kilojoules of energy, which is more than enough to compensate for what we need to pop that phosphate onto glucose. So as long as the overall delta G is negative, reaction proceeds, it's favorable and spontaneous. We'll also see an example of this in the last step of glycolysis. There is part of this half reaction where we go from this kind of enol looking arrangement to a keto looking arrangement. This step from enol to keto releases about 60 kilojoules per mole. That's a lot. The other thing that's happening in this reaction, you see, is that we are chopping off a phosphate and using this phosphate to make ATP. So the other part of the reaction that's happening is combining a DP plus a phosphate, but that requires 30 kilojoules of energy. Well, by coupling these reactions together, we have an overall negative delta G, and this reaction is favorable and will proceed spontaneously. So the story, folks, is as long as the overall reaction has a negative delta G, it will be spontaneous and favorable. And that is true for any phosphate transfer. For the movement of one phosphate from one molecule to the next molecule, the overall delta G just needs to be negative. And so what you can do in a table like this, or on the next slide as well, is you could take a phosphate from any of these higher energy molecules and transfer that phosphate to create any of these lower energy molecules, as long as the overall delta G is still negative. Now, why do we call some of these molecules high energy while some of them are low energy if they all contain these phosphoanhydride-like bonds? Well, we can just keep in mind that some are more high energy than others for the three reasons we discussed. Maybe there's more resonance upon hydrolysis or more charge separation for some of these molecules compared to others. And here is another table for you to look at that just kind of lists the delta G of hydrolysis for a bunch of molecules that contain phosphoanhydride bonds. You can see that some are much more high energy than others. Up next, we're going to learn about another high energy molecule.